What we want to reflect upon now are some of the sets of numbers that we use. Now, there's a lot of history in how human beings have developed these sets of numbers, and it's not really linear. Human knowledge was shared across many cultures along with trade, and our system of mathematics has roots in India, China, Greece, Africa. All the cultures that mixed around the spice routes shared parts of their mathematical knowledge. We tend to look at the Greek tradition for how we got these, but anthropologically, the development of number systems is similar across most cultures. So we're just going to look at some characteristics of these. So the first thing we'll look at will be natural numbers, and their cousins, the set of whole numbers. Natural numbers we tend to write with a double stamped N, and it's a set that starts with 1 and continues off forever. Whole numbers, which gets a double stamped W, starts with 0 and goes off towards infinity. A characteristic of these are they have a starting place and they have a gap between the numbers, and that gap is always of a fixed length. In our case, it's a unit, and the unit in these numbers is 1. So any number really gets constructed by a new number. So if I'm on 2 and I want a new number, I add the unit. If I'm on 8 and I want a new number, I add the unit. And there's a lot about the naming conventions we've had for natural numbers, different base systems, but for the collection of entities as a quantity and the quantity they represent, we can look at these numbers as being the ability to add 1 to create a new number. What ends up happening is if I look at what I can do with numbers, so I can talk about any number plus a new number will equal some third number. And what we want to do is we will say that these numbers m and n exist within natural numbers. Well, we run into a problem that if m is 1 and n is 1, x doesn't exist within natural numbers. I don't have anything I can add to 1 to get me 1 back. But if we go to whole numbers, that gives us the concept of the 0. So we'll take the same concept here, and I'll say we're within whole numbers. Well, now I run into the problem that if I'm going to add this 1 and I'm going to get to 0, well, x is now not within whole numbers. And so a new set of numbers gets built to deal with this. Basically, the problem of this equation not being able to be solved completely with whole numbers. Makes us create new sets of numbers. And we're going to work our way through sets of numbers to get an idea of why we end up creating different number sets and some of the problems that were introduced or solved with them. And so the solution is we're going to come up with integers. Right? Integers are what we create. And integers get a double typed Z. And I've used integers already. Well, that's defined as 0 and positive or negative numbers. And now we really have this set that goes from negative infinity to 0, and then from 0 out towards positive infinity. And in a way, we can think of this as an origin, and things on this side are the positive integers, and the things on this side are the negative integers. And so this lets us solve this. X plus m equals n, where m and n are integers. Well, this can be solved completely within integers. And we'll talk about what makes a set complete under certain operations. But now we can do addition, and we never have to leave the set of integers. And that was an extremely useful tool. I think historically we tend to see this being developed when the concept of debt entered into agricultural stores in early agrarian cultures, that they needed negative numbers to talk about what was owed. But let's look at the next equation that we can have a problem with within integers. And so we've created integers. We can do additions and subtractions now across the scope of negative infinity to positive infinity, but we run with this problem. A can't be 0, and A and B will exist within integers. Now, why we say A can't be 0, I guess we can look at it this way, right? We can't divide by 0. It's undefined mathematically in division. If we look at division as cutting things into parts, right, that's one thing. I cut it in half. I could say, if I had this big thing, A divided by 2. But if I have something, how do I cut it into 0 parts? And since it doesn't make sense within that viewpoint of division, or let's say I have 4 things, and I want to divide the 4 things into 2 sections, I have 4 divided by 2. But if I have 4 things and I want to divide it into 0 groups, again, the definition doesn't work. And so we say division by 0 is undefined. But we want to talk about this thing that gets created here. Well, this looks like a fraction. And division and fractions are related. And what the ancients needed to do is they needed to make rational numbers. And so what they did is they make a set of Q for quotient, and they define it as it's A divided by B, such that A and B are integers, and B can't be divided by 0. And so we get this new set of numbers that come about that solve the multiplication problem. Now this equation, AX equals B, as long as A does not equal 0, A and B can be these new rational numbers. And we have fractions. And a weird thing happened to our set. I can't write the set out because I can have from negative infinity down to negative 1/2, negative 1/4, negative 1/8, 0, 1/2, 1/4, 1/8, up to positive infinity. Well, I can wedge a third in here. I can put 2. Let's see, over here, 2/15, right? There are an infinite amount of numbers that can be wedged within here, and so we have to use this rule as our way of describing our set. And to be honest, the rational numbers really, really worked for most of the ancients. A lot of mathematics could be done exclusively with just rational numbers. Now, rational numbers is our first field that we'll look at, but we're going to define the field in the next lecture. What we want to look at is a problem with rational numbers. And we'll talk about infinities in another lecture too that arise from this. We run into a problem that the Greeks recognized, Pythagorean's followers recognize this, that if I have a square of unit 1, then in what is the diagonal? And so using the Pythagorean theorem, where c is the diagonal, we have 1 plus 1 equals c squared, or c equals the square root of 2. And so the length of this is fixed. You can build this. I can build a square, I can cut it diagonally, and if the unit side is 1, then that diagonal has the exact length. This is measurable. And so Pythagoras believed that everything was perfect ratios of numbers, perfect quotients. And so they wanted to find the fraction that this was. And so let's look at what happens if we try to find this fraction. So what we're going to say is we're going to assume that the square root of 2 is equal to a fraction p over q. And p over q is reduced. What we mean by being reduced is 2/4 reduces to 1/2. That anything over the top and bottom has been canceled out of it, so it's in this reduced form. And so they wanted to find what this p over q was. And in the process, they found something neat out. So what we're going to do here is we're going to do the things we can do with numbers. I'm going to square both sides. And then I'm going to multiply both sides by q squared so that I have a relationship between p and q. Now what's nice about this is 2q squared is always even. Right? Because we can say 2 times any number is always an even number. That's how we count by 2s. 2, 4, 6, right? If a is 1, then this will give me 2. If a is 2, it gives me 4. So we know p squared is even. And that's really, really nice because there's something about squaring even numbers. So if I take an even number, I'll write my even number as 2a. And I square it. I get 4a squared, which is 2 times 2a squared. So if I start with an even number, I will only get an even square. And if I start with an odd number, this part here is 2 times 2a squared plus 2a, which is also an even number plus 1, or odd. So if I square an odd number, I always get an odd square. If I square an even number, I always get an even square. So we know p is even. So for the square root of 2 being some fraction, the number upstairs has to be even. And we can write this as p equals 2m. So I'm going to come up here, I'm going to take p equals 2m, and I'm going to assert it into here. So what this says is, so I'm going to take this, combine it with this, and we'll come over here for a little more space. So 2q squared is equal to 2m squared, which is 4m squared. I'll divide both sides by 2. And lo and behold, q squared is even, which means q is even. And so I can write q as 2n. That means this number here that I was looking for is 2m over 2n. But I have a problem. Those 2's are going to cancel. This is not reduced form. And if I reduce it, m over m doesn't work. I'll come back with the same problem and have to get the 2's. And so I get a contradiction. And so what the Greeks learned was that you could not write square root of 2 as a rational number. You could not write it in the form of a fraction, which includes our decimalization. And so we created a new set of numbers, irrational numbers, and we mix them with the rational numbers. So if you take irrational numbers and the rational numbers and you put them together, we get a set of real numbers. And what that did is that made a number line that runs off to infinity where there were no gaps in it. Right? The rational numbers has gaps. There was a place in the number line with rational numbers you couldn't put the square root of 2. And we have a whole bunch of irrational numbers, right? Things that we cannot represent clearly by fractions. And so real numbers really are the numbers that we tend to work with a lot in numerical algebra that you've studied before. And real numbers do the meat of the work. And we call them real because if you go back to when I said we can build this square with this measurable length, it's real and measurable. And so we have this set of numbers that can do a lot of work for us. All right, so in my next video, we're going to look at where real numbers fall down, and we're going to build some complex numbers out of that, and then we're going to do some work with complex numbers.